Calculus 30, we're in section 8.2, we're talking about derivatives of exponential functions. And first of all, an exponential function is where we have an x in the exponent position, hence the term exponential, okay? X is in the exponent term. Two common exponential functions that you've seen before, y equals 2 to the power of x, y equals 3 to the power of x. There would also be a y equals 10 to the power of x in there. But these are what exponential functions generally look like. And for the purpose of our lesson today, we're going to be talking about derivatives of exponential functions. And most specifically, the derivative of a special exponential function that has a special base. And there's one particular base that is not 2, it's not 3 or 5 or 10, but it's a special base that gives us an opportunity to do calculus really easy on it. And I'll explain that in a second. So there's a special base that we're going to be working towards. Now, in order to find the derivative of any function, you know that back from the, this is the definition of a derivative, right? The limit as h approaches 0 of f of x plus h minus f of x over h. So this is from chapter 1, from the very first part of Calculus 30 that we learned. So if we were to put in an exponential function, and in this case over here, they just wrote in bx, b to the power of x. That's any base. So watch what happens when we try and find the equation for the derivative of an exponential function with base b. So the function is b to the x, and so this would be b to the x plus h minus b to the x. Now, this is really critical. One of the most important properties of exponentials is that when you have an exponent and there's a sum, an addition there, that can be split up into a multiplication of two exponential parts, right? So b to the x plus h can be split up into b to the power of x times b to the power of h. That's really important. So when that happens, okay, what we see is that we can now factor out a b to the power of x. And that really is a constant because that's a regular base term like 2 or 3, and to the power of x would be a number as well. So it's going to be kind of like it's going to be brought out because h is not in there, right? So we can bring that out. And this is actually really important. It maybe doesn't look too important right now. But what's really cool about this is that the derivative of an exponential function with base b is actually has the original function in it. Okay? So the original function is part of the derivative, but it's actually separate. So what we need to do is we need to focus on what is this piece all about. Okay? What is this piece all about? Well, if we work with y equals 2 to the power of x and we find the derivative and we plug in, literally if we test little h values like b to the power of 0.001 or 2 to the power of 0.001 minus 1 over 0.001, we could actually do that and we could get values. And I'm going to show you a table here in a second. I think I got to zoom out a little bit. I'm going to show you this table down here, and I'm going to kind of move down here a little bit. Try and get all this in the screen so you can see it. Okay? But look at this table down here. So if we use y equals 2 to the power of x, and I want to find the derivative is going to be 2 to the power of x times something. And if we use this limit, or evaluate this limit as h approaches 0, look what happens when I have a base of 2 here. See that? So at 0.1, so that's 2 to the power of 0.1 minus 1 over 0.1, I get this number. And then as I get closer and closer and closer to 0, it starts to center in on something about 0.693. Okay? And so our limit is pretty close to 0.693. And what that means is that this 0.069, about 3, is the constant that you multiply the original function by to get the derivative. Okay? So again, let me just be clear. The derivative of y equals 2 to the power of x is actually equal to 2 to the power of x times 0.693 or somewhere thereabouts, a constant. Okay? Now, if we did the same thing with 3, and we evaluated, again, this limit right here, and I put 3 in for the base, you can see that the limits as x approaches 0 comes to about 1.098 or so, near 0.97, 0.98. So 1.098 or so, okay? That's the constant by which the original function is multiplied to get the derivative. Now, why is that important? Well, it's important because when we're talking about calculus, we often work with derivatives. And if we're trying to choose a function to represent some kind of population growth or some kind of exponential situation, something reproducing, or if it's bacteria or something that's growing over time in an exponential fashion, it would be helpful for us to be able to choose an exponential function that has a base that makes calculus easy. Because we all want to make calculus easy, right? Yeah. So here's what I'm getting at. If you examine the bases of 2 and 3, what we find is that somewhere in between the base of 2 and 3, like 2 point something, there logically should be a base that is multiplied by the constant 1. Or there should be a base for an exponential function which is its own derivative. So y equals some b, that's between 2 and 3, to the power of x. When you take the derivative of it, it would be that same base to the power of x times 1. Okay? And there actually is a base that's in between 2 and 3, and it is called e. Now, you've seen on the AP questions and some of the AP exams that we've studied and looked at, you've seen e, right? Well, e is this special base because when you evaluate this limit with this special number e, this becomes 1, okay? So the constant there is 1. Now, I'm going to try and back this up a little bit with some Desmos here, okay? So I've got this ready for Desmos. So you can just drop your pen if you want and just watch here for a second. But what I've got is, I've got f of x equals a to the power of x, and I've set a here to equal 2. So the red graph is, this red graph is y equals 2 to the power of x, okay? What I've also got here, which you might not be able to see if you're watching the video off screen, but g of x here is the derivative of f of x. So this is graphing the derivative. So y equals 2 to the power of x has a point here at 0, 1, which most exponential functions do. Look at the derivative value. So again, if we have the derivative here, look at what the derivative value is. At 0, the value of the derivative is 0.693. Going back to our notes, 0.693 is this constant here that we kind of determined, right? So what am I saying? Well, that if you take any value of the function, like here this is the 0.12, right? So the derivative should be about 0.693 times 2. So if we drop down here, so we should have 0.693 times 2, it would be about 1.386. You see that? So everything is about 69% the value, okay? Or times 0.69. Now what about 3? If I move this up to 3, look at, here's 3. There's 3. So each value, so here at 1, 0, right? The value for its derivative should be about 1.098 or so above. Well, what's the, look at that, 1.099. You see that? So the derivative of y equals 3 to the power of x is almost the same as the original function. So watch what happens when I draw the slider down a little bit. There becomes a function that equals its own derivative. So the derivative of y equals about 2.718 or so. The value of e, it is its own derivative. So whatever the y value is, okay, for this, 0, 1, the derivative is the same as y value. whatever the y value is over here, that is now equal to the derivative. Okay? So, back to our notes here. I've got this little explanation here. So this is a summary of just what we've kind of been trying to explain here. So the base e, and that is approximately 2.71828, and it's irrational, it keeps going on forever, but that's about what the decimal is about, somewhere around there, is the base of an exponential function that's very special in calculus. It's special because y equals e to the x is equal to its own derivative. So when you take the derivative of e to the power of x, that is y prime of e to the x is e to the x. They're the exact same. Okay? Now let's think about this. I'm just going to show this graphically now. The y value is 1 here, so guess what the slope of the tangent line is at this point?
1.
It's 1. The y value is 3, so guess what the slope of the tangent line is at this point?
3.
3. The y value is 7. Guess what the slope of the tangent line is at this point?
9.
It's not 9, no. It's 7. Yeah. You getting it? So the y value of this function, y equals e to the x, is the derivative of the function. Okay? Now that's something that's really special in calculus, because let's say you want to model some population growth, and you have like y equals e to the power of 2x or something. Well, taking the derivative of that now, finding an instantaneous rate of change, becomes actually really easy. It becomes super easy. And it's not really easy, as you can tell by this up here. It's not really easy to go from the definition, let's say, of a derivative and have to do the derivative this way. That's not easy, right? But if we can say, hey, y equals e to the x, what's the derivative? Y equals e to the x. It's itself. Then you're good to go. Question?
So in order to solve problems, can you just take the value and times it by 1.69? Because that's how much it increases by?
Well, okay, so if you're talking about y equals 3 to the power of x, or 2 to the power of x, I'm not sure where that 1.69 you said? 1.69?
Because you said it's increasing by 69%, right?
No, on this y equals 2 to the power of x. Okay, so let's go back to Desmos there. Y equals 2 to the power of x. If I brought this down to 2, okay, that's 2.1, 2. So that if this is the y value right here, 2.116, let's say, or 111, then the derivative, the slope of the tangent line at this point would be exactly 69% of whatever that value is. So that would be the slope of the derivative. So this purple line here is the graphed derivative of the red line. Right? So as I move up, you see there is some point where they become the same graph, and that is the point E. So if I went over here and said, I just typed in E, 2.71828, they're the exact same. Okay? So it's its own derivative. So that's what E is all about. Now, when we're now working with this, so like I said E to the power of 2x is actually pretty easy to take the derivative of. All we have to do is remember the chain rule. So if you have y equals e to the power of 2x, then you want to find y prime with respect to x. Well, it's just the exact same thing multiplied by the derivative of the inner function. Y prime is 2e to the 2x. That's it. Okay? So if we have y equals, and I'm just going to write a little summary note here, if this is some constant to the power of x, then the derivative is this constant times the original function. Okay? So whatever that constant is, it's just like it's brought down kind of in front there. That's just a kind of a general rule there for you, and you'll see that in your textbook as well. So let's do it. Let's do a different one over here. Okay? So y equals e to the power of 3x squared. Well, again, if it's an e function, yeah, no problem. The derivative is the exact same function with all of its warts and pimples and everything, just write it all in there, times the derivative of this inner function, which is 6x. That's it. So 6x times e to the 3x squared. That's your answer. Okay, so just remember the chain rule, and finding the derivative is actually pretty easy. A good point is, don't take the derivative of the outside function and the inside function at the same time. Make sure you split that into two parts. So, yeah. Good. Any other questions you might have? Okay. Okay, so in the lesson, I will point out another video here. 3 blue, 1 brown. It's some good math stuff. Some of it will be maybe over your head. It's got a lot of high-level stuff. But there's actually kind of some neat things that he does here in this. Now, I don't know if I want to go quite there yet, but in his explanation of what E is and the importance of E, kind of neat. So you can look at this on your own if you want, but there's a certain part that I kind of wanted to show you here. Okay, so I'll just keep this, maybe the volume off here. But this is the e to the power of x, you see. So whatever the y value is equal to the slope there. E to the 1, that's the slope. E to the 1.5, that's the slope. E to the 2, that's the slope. Okay? So just that little graphic there, you see that sliding about. And of course, I guess maybe I will just fast forward to this part right here. So there is a connection. You don't really need to know about this right now, but do you remember how when we're finding the derivative of 2 to the power of x, there was that constant right there? There is a special relationship between these constants for these different bases. And that comes in that this number right here is something called the natural logarithm of 2. It's not in. No, that's an L. That's a small L. It's the logarithmus naturalis. It's the Latin, and this is the natural logarithm. So I will point out this. I don't know if this will be an official part of this lesson, because I think that might be for next time, which we'll get into next time. But the Ln that you might see in your textbook is related to the base E, and this is just a teaser for next lesson, that the logarithm with a base E, okay, is equal to the natural logarithm. So this log base E is where the natural logarithm comes from, and that's going to be in the next lesson, in 8.3. All right, so if we look at these numbers, now watch this. This is important, guys. You ready? Now you may be saying, well, what if we have to use a function with a base other than E? Well, the reality is that any exponential function can be written as a variation of the function with a base E. So watch this. So 3 to the power of t, and 4 to the power of t, and 5 to the power of t, and so on, can be written as a function of with a base E. So this is not a deal. If you're like, hey, we need that exponential graph to go up a little bit steeper there, we can't use E as a base. Well, you can. You just have to, you have to adjust this. So this number here would actually be the exact same as if you were dealing with a base of 6 and so on. So I just wanted to show you that just in case you're worried that, hey, well, now we're limiting ourselves to a base E, well, really, any exponential function can be written as a base E, and you have no problem. Okay? So sorry?
How do you do that?
So how do you do this? To connect this to, so if you want to write the y equals 6 to the power of x, and you want to write that in base E, then this number, remember from this previous little graphic that I showed you, this number would actually be the natural logarithm of the base that you want. Let's test that out. So if we go back to, where's my Desmos? We go back to Desmos here. So let's say we have the base here now is, oh goodness, what have I done? Add a slider. So the base is y equals, let's say it's 6, okay? There we go, it's 6 now. Okay, I don't want the derivative. But if I were to now say, okay, y equals, I'm going to make the b equal to e, okay, e, right here. And I'm going to make some kind of constant k, and I'm going to make k equal to ln of 6. I don't know if this will just do ln of 6 here. Yeah, ln of 6. So do you see how those graphs are equal? They're the same? Now they actually are the same color, which is a little bit tough to to see. Let me make it a different color, black maybe. Okay, but you see, they are the exact same graphs. So y equals 6 to the power of x is the same as y equals e to the power of ln of 6 to the x. So you can make any exponential function you want with base e. And next lesson, you're asking good questions, but next lesson I'll talk more about the relationship between e and ln, okay? And this will be even more clear after next lesson. All right, here's your assignment.
Tomorrow when he comes back.
All right, whatever. I don't believe
Yeah,
you.
he's with
Okay.
his wifey right now. But
Okay, so here is your assignment. You should have your textbook, but if you don't have your textbook, I will just display this a little bit here for you so you can see this page or two.
biology test
Simplify
tomorrow,
2
I haven't
over
studied
10
for
and
yet.
negative x.
Would you whine a little bit more?
Have you guys studied for biology yet?
That's kind of a.
Tonight thing?
Isn't that
Yeah.
just 2?
Or Victoria this
Isn't
morning
it
kind of
just
thing.
Tomorrow morning.
negative
Haven't you